Now we have already discussed like the rate of energy flux due to the convective transport. Now as we have written for Vx, we can write similarly for Vy, which is going to be half rho v square plus rho u cap Vy into ds, because we are taking the same particular area. Obviously this will vary, this can vary actually. 1 by 2 rho v square plus rho u cap into Vz ds. Now what is this? It is the rate of energy flux due to convective transport in y direction. In the similar way, this was for x direction. And this is for z direction. So we can write a generalized form, general form for the, I will say energy flux right now, not rate, energy flux. So that can be written as like 1 by 2 rho v square plus rho u cap into v. Now this v can be either vx, vy or vz. Now it depends on whatever you want to do. So we have basically found the convective transport. Now we will go to work associated with the molecular motion. We will go first of all with what is work. Next heading would be work which is associated with molecular motion, with our molecular motion. Now why this? Why is the work with the molecular motion? It's obvious, we discussed before. There is going to be a shear stress introduced, which is the momentum flux. And due to molecular motion, there is only one thing, momentum flux. So it's going to be due to shear force, due to shear stress rather, due to shear stress, which indeed give rise to what? Which give rise to viscous forces. So let's suppose that a force is acting, that is known to be F, at a particular distance of, because it's a shell, so we will take dx. So what will be work done? Work done is nothing but force into distance, so that is going to be force into dx. F dx will get work, and definitely it is done on a small distance, so that is going to be dw. Now suppose we have to write rate of work done. So rate of work done, how can we write? We can divide by dt on both sides. Dw by dt is equal to F into dx by dt. Now dx by dt is indeed, there is one quantity changing with x direction. In this direction, velocity is changing with time. So obviously this is going to be v. We can write that dw by dt is equal to fv. We have our basic equation written as this. Or we can write this equation as something if we divided both sides by area. So that is going to be 1 by a dw by dt is equal to f by a into v. F by a, so that is going to be force by area. Now what's that? We can represent that with tau, F by a. So like we can go with this, F by a is nothing but tau. So work done, because we divided with area, so that is going to be work done per unit area. That is going to be 1 upon a dw by dt, I think it is the rate of work done, rate of work done per unit area, that is going to be nothing but tau into v. This is another our important equation. Now we have got to this conclusion, like that is tau into v. Now we know one thing, that flux into area will give me nothing but force. That's a pretty obvious thing. Now we can go, what is this called? Pi. We'll call it as momentum flux. That's basically molecular momentum flux, rather. It's momentum flux, but what? Molecular momentum flux. Molecular momentum flux. Now, suppose I write pi x. What is the meaning? That is molecular momentum flux in x direction. We are taking this particular thing in x direction. Now we know force is flux into area. So suppose we have to go force which is exerted in x direction. So that would be pi x into ds. No doubt. Now we'll have to find rate of work done. Suppose you have to find rate of work done. So all you have to do is multiply it with velocity. So that is pi x v ds, or it would be vx. Pi x vx into ds. Now you have to go for per unit area. So let's assume we have to write rate of work done per unit area. So that is going to be pi x into vx. So we have got the equation previously, pi x dot vx. Now we can write it in general as pi dot v for any component. Suppose we are writing for x component, then it's going to be nothing but pi xx into vx plus pi xy plus into vy plus pi xz into vz. Similarly, for x pi dot v in the y direction, that's going to be pi yx into vx rather plus pi yy into vy, and that's pi yz into vz. Another we can write it as pi dot v into z. For the z component, we are going to have pi zx into vx into vz. No, it's vx only, vx plus pi zy into vy plus pi, that's going to be zz into vz. Now we know one thing, that pi xx is nothing but p plus tau xx, where p is nothing but pressure momentum and tau xx is nothing but x momentum transported in x direction. We can go for pi yy in the similar way. That's going to be p plus tau yy. Obviously this is pressure momentum in y direction and y momentum being transported in y direction. Similar way, pi zz, pressure momentum in z direction plus tau zz. Now you can write it in this form, that whenever there is going to be something like delta of delta ij, I is equal to j, it's going to be like this: pressure is equal to p, else in all cases pressure term is 0. Basically it means that here it is pi xx, that's why we are writing pi plus tau xx. But suppose if it comes to be pi xy, then we will not write this pressure term, it will be neglected. We will take it as tau xy. And why it will be neglected? because the basic form involves a delta operator, which is nothing but a Kronecker delta. Kronecker delta. Now, since we know that Kronecker delta is of utter importance, so let's try to write these formulas in form of Kronecker delta. So that's going to be pi dot v. I'm writing in a generalized form, delta x pi x into v plus delta y pi y into v plus delta z pi z into v. Now whenever delta, it is written delta x, you can write it as delta ij. Now whenever there is a delta xx, it is going to involve a pressure term. Whenever there is delta yy, it is going to involve a pressure term in y direction. And whenever there is delta zz, that involves a pressure term in z direction. Else, all other things are going to just involve the shear stresses like tau xy, tau yy, tau yx, and tau yz. Now let's go with this. Now this particular thing we have obtained is nothing but viscous heat. The source which is due to the viscous heating or due to friction of the layers. And our major equation means this is one flux, this is viscous heat flux. Previously we did obtain a convective flux, which is this, like we wrote this general form, energy flux. This is a convective energy flux, and the next term involves a conductive energy flux. So we can denote this as E, small e, which is the combined energy flux. So let's write it as combined energy flux. Combined energy flux, which is nothing but a summation of all these. So E is equal to viscous heat flux. So first of all, we will write this convective heat flux, rho v square plus rho u cap. This is going to be nothing but the convective heat flux pi dot v. As we have studied, this is the viscous heat flux. The next is conductive Q. Now this Q can be determined. This is conductive heat flux. So obviously this has some relation to do with conduction, and the governing law of conduction is nothing but Fourier's law. Fourier's law. Now we'll take like Fourier's law. What is that? That is Q is equal to minus K dt by dx. So we have put this here, and we will get a combined energy flux. Now suppose that we have a shell here between two plates. Suppose this is an outer plate, this is the inner plate, this is of the outer cylinder. And this is inner cylinder wall. Now why we had to take a combined energy flux? Because here it will exert a shear stress, and that will give rise to viscous heat dissipation, viscous flux due to the friction. Now there will be another flux due to the transfer of kinetic energy. Transfer of kinetic energy, that would give you a convective flux. And since wall is there, so there will be a heat flux as well, conductive heat flux Q, which is a conductive heat flux. So there is no sense in taking an individual balance. You have to combine all these fluxes and then take the balance. So we have obtained combined energy flux. That's the reason why we did all this. Combined energy flux. Now we will go once again back to the shell energy equation. So that's shell energy balance. Now this will be modified because now we have to take combined energy flux. So suppose there will be some combined energy flux in and some combined energy flux out. So that is going to be rate of E in, basically combined energy flux in, minus rate of E out, combined energy flux out, plus the rate of work done. There will be some external forces. There might be a pressure or a gravity. Rate of work done by external forces. Like gravity or pressure, and there will be some sort of rate of energy production. There might be some energy produced. Like in this case, viscous flux is viscous energy, viscous heat is produced. There will be rate of energy produced, or we will call that rate of energy production. So since it's steady state, accumulation is zero. Now we will go to a very smooth example because we will now need to learn what is happening here. Suppose this is our outer shell. Let's assume this particular thing, this is our outer cylinder. Let's assume this is our inner cylinder, and a particular fluid is filled between these two. So this will, if we make it, that's going to be this and this. Suppose that the outer is having a radius capital R, it's B, and the smaller one is having radius small r. B is the gap between these two. And let's suppose that the outer cylinder is made to rotate with an velocity omega. Obviously it's r, so the velocity would be omega into r. So now we have the velocity omega r. Now suppose we are taking this plate and this plate. I think we will understand better from here. Suppose that the fluid is filled between these two. This is the wall of inner cylinder and this is the wall of outer cylinder. So let's assume we are taking only this region, only this particular region. So the upper plate would be this, and the lower plate can be denoted as this. So let's assume that we are having a Cartesian coordinate system. So the coordinate system that we are taking is not cylindrical but Cartesian because it will help in our calculations. Cartesian coordinate system. Now this is x direction and this we can denote as z direction. So there will be a change of velocity, obviously, because the fluid which is closest to this part, means the outer cylinder, is having more velocity, and the fluid which is closest to the near cylinder is almost having zero velocity, or is having zero velocity actually, and the upper fluid is having a very small velocity as compared to the upper plate. So now how would be the velocity profile? Assuming that the velocity variation here is linear, we can write this thing as Vz is equal to Vb x by b. So a linear velocity profile. So it is basically zero here and it is going to be maximum here. Obviously a Cartesian coordinate system, so this type of velocity profile will be obtained. Now this is what we have got about the particular velocity profile. Now we'll have to dive a lot deeper into this. This is our stationary surface. And this is our moving surface. Or I would rather say rotating surface, moving surface. Now we know two things. First of all, we know the velocity profile and we know that work is equal to nothing but force into velocity. And further we can write force as flux into area. So from this we can get work done. That is going to be flux into area into velocity. Now what is going to be the area of this particular thing? So the gap is B, Length of this plate is L, and let's assume that the width is W. So let W be the width. Obviously the area of this particular system is going to be WL, W into L. And what is the flux? Flux is going to be tau xz, but with a minus sign. Now, and velocity is VB. VB is what? The velocity of rotating cylinder. It's VB here. So now, but why the minus sign is here? So let's assume a surface. We will explain why the minus sign is here. The upper plate here is moving with a velocity VB, but the lower layer, it is going to drag this upper plate, but I'll rather say it is going to put a force. Now the force, due to this force, the velocity of this will tend to decrease, and this is having a negative impact. So the force is acting but in a negative way, so that's why the flux taken here is negative. So rate of work, that would be minus tau xz VB WL. That is what we have taken. Now suppose we have to get per unit volume. So volume of this, volume would be WL into B. Now rate of work done per unit volume. That's going to be minus tau xz VB WL upon me WLB. So this gets cancelled out, and it's minus tau xz VB upon me B. Now we know how to write minus tau xz. That is going to be minus of mu, or minus it would be plus, so obviously it's plus mu, dvz upon me dx plus dvx upon me dz. Now we need to know which velocity is 0 and which is non-zero here. So the velocity here we have taken in this direction. So from the velocity profile we can see that the velocity non-zero is z. Vz is non-zero. Vz is non-zero. So Vz is not equal to 0. Vx is 0 and even Vy is 0. Why? This is a 1D flow. This is a 1D flow, meaning that only Vz will be non-zero and X and Y will be 0. For X, this is a fully developed flow. Now, whose function is this? There is velocity in Z direction. Vz is a function of X direction only. Why? Because we can see here that Vz is changing with respect to X. At this point the velocity is this. At this point the velocity is this. So Vz is a function of X only. Now Vz is not a function of Z direction. Why? Because it is a fully developed flow. Or you can say that R is very greater than B. So curvature effects are neglected. Curvature effects are neglected. And the next part of this is that why Vz is not changing in Y direction? Because the width is infinitely large. Width is very large. Because you are taking a shell, you are taking layers, you are taking liquid layers. Obviously the width, you cannot determine the width. Liquid layer width is very large. You cannot respect. Even there is a change, that is very negligible. That is negligible. No one knows what that change actually means. So we will need this. Now see, Vx is 0. Obviously this term turn out to be 0. Vz is there and Vz changes in X direction only. So tau xz, that would be mu dou vz by dou x. This is what we have acquired, and that is equal to mu dvz by dx into vb, and this whole term should be divided with b itself. This is what we have acquired. Now vz is nothing but what? Vz is this thing. Vz is vb into x by b, because velocity profile is linear. We're taking a linear velocity profile. So vz is vb x by b. Now we have to get dvz by dx. So dvz by dx, that would be vb by b. Name it as equation 2, and we have equation 1 here. So let's put this value here. So dvz like here, suppose you have put mu, so that is mu vb by b into vb by b into vb by b. That's nothing but mu vb by b whole square. Now this is the energy in form of heat. Obviously we have taken that due to shear stresses, this is released, so this is in form of heat. Now we will go to our case 1.